Hello, everybody. So it's time for the next Physics 328 video. This time, what we're going to talk about is, again, the motion of a symmetric top. But in this case, it's not going to be a free rotation where the net torque is 0 on the top. This time, we're going to have one point fixed, and there'll be a gravitational force acting on the center of mass. We will try to describe the motion of this top from the perspective of someone in a fixed reference frame. So if you're looking for this topic in the textbook, it is section 11 in chapter 11. And we're not going to do everything that's in that section, but we'll do some parts of it. And then, in fact, what I'm going to try to do is use those results to explain one of the demos that we did in the first day of class. One of the demos we did was the bike wheel, where we were going to suspend it from its axle from a string that was hanging from the ceiling, and we suspended it while the wheel was spinning. And what we found is that the bike wheel didn't tip over. It stayed level and started to precess or rotate around that string. And so we're going to see if we can describe that demo mathematically. Okay, and so here's the picture. We're going to have our fixed coordinate system. And so remember, our fixed coordinate system was the primed system. So we have a vertical z prime axis, and we're going to say that this is our fixed inertial reference frame. So our fixed coordinate system. And then let's put a y prime and an x prime. So there's our fixed coordinate system. We'll draw a top, and so my top I'll try to draw a simple one. It has some disk, let's say, and then that disk has an axle that extends along this axis, something like this. Okay, and what we'll have is we'll have a rotating coordinate system that's aligned with the principal axes of our top. And so one of those principal axes will be the symmetry axis. And so we'll call this the z-axis, and this is our symmetry axis, which is in the rotating frame. Okay, this is also the axis that we called the E3 hat axis. So the third principal axis is along our symmetry axis. Okay, there is a net force acting on our top. And so let's say our center of mass is somewhere here close to the disk part of the top. And so there is a force mg acting on our top. And let's make the distance from the origin to the center of mass h. Okay, so h is the distance from the origin, which is where our fixed point is, to the center of mass. All right. If you recall, we had a picture of Euler's angles, and maybe I should just bring it up here. And so let's see if we can find this thing. Our favorite picture, which I'll bring up at least one other time in this video. What I wanted to highlight here was that what we've got is our x3 prime corresponds to our z prime axis, and then x3 corresponds to our z-axis, and the Euler angle theta is the angle between these two axes. And so that means that this angle here is the angle theta. Okay, and if we extend back to the z prime axis of the fixed coordinate system, the height of the center of mass above the x prime y prime plane is h times the cosine of theta. Okay, when we analyze this problem, what we're actually going to do is we're going to set up a Lagrangian. And so the Lagrangian, as you know, is the kinetic energy minus the potential energy. So the potential energy of the top is a gravitational potential energy, and it's just equal to mg times the height above the x prime y prime plane, which is h cos theta. Okay, so that's the potential energy. We have a symmetric top. So for our symmetric top, we chose the third principal axis is the symmetry axis, and so we'll say the rotational inertia I3 is equal to IS for symmetric. And then the other two principal axes are perpendicular to the symmetric axis, and so they have the same rotational inertia, which we're just going to call I. So this is a symmetric top. Okay, good. So let's just try and start to construct this Lagrangian. What we'll need is the rotational kinetic energy. And so that's going to be 1/2. Well, what it would be is I1 omega 1 squared plus I2 omega 2 squared plus I3 omega 3 squared. But we've already said that I1 and I2 we're just going to call I, so we get 1/2 I omega 1 squared plus omega 2 squared. And then I3 is IS, so we get 1/2 IS omega 3 squared. Now I guess it was probably two videos ago now that we wrote omega 1, omega 2, and omega 3. This is the angular velocity in terms of components along the principal axes. We wrote those components in terms of the Euler angles. So in terms of Euler angles, if you look back, what we had was that omega 1 was equal to phi dot sine theta sine psi plus theta dot cos psi. And what we need in our rotational kinetic energy is the square of this. Okay, so if we just expand the square, phi dot squared sine squared theta sine squared psi, then we have a cross term. We're going to get two copies of that cross term, phi dot theta dot sine theta sine psi cos psi, and then we have plus theta dot squared cos squared psi. Okay, we could do the same thing for omega 2. Well, first let's just write down omega 2 and then we'll square it. So omega 2 was phi dot sine theta cos phi psi, minus theta dot sine psi, and then we want to square that to construct our rotational kinetic energy. And so doing the same thing, phi dot squared sine squared theta cos squared phi, and then the cross term is minus this time 2 phi dot theta dot sine theta cos psi sine psi, and then our last term we have a negative squared, so we get a plus theta dot squared sine squared psi. Okay, what we need to do is we need to add omega 1 and omega 2 squared. So we have omega 1 squared plus omega 2 squared. Okay, so the first thing we can do is we can say, look, we have phi squared sine squared theta and phi squared sine squared theta. And when we add those up, we'll end up with a sine squared plus cos squared, which is 1. And so what we're going to get is, let's say from the red terms, when we add them up, we get phi dot squared sine squared theta. Okay, then what we can do is we can compare the, let's compare the cross terms. 2 phi dot theta dot, and we have minus 2 phi dot theta dot. Then we have sine theta, cos psi, sine psi, sine psi. So they're identical except for the sign, and so when we add them up, we get an exact cancellation. And then the last term is a theta dot squared and a theta dot squared, and then we get cos squared psi, sine squared psi, which again, we factor out the theta dot squared, and we get cos squared plus sine squared is 1. And so we get just a plus theta dot squared. Okay, so that's good. What we have to do also is we have to do the omega 3 squared. So omega 3 is equal to, if you look back 2 videos ago, it was phi dot cos theta plus psi dot. And then we have to square that as well. Okay, so then our kinetic energy, which is all rotational, because we're imagining the point of contact with the ground is a fixed point, so there's no translation. So we get a 1/2 of I, and then it was omega 1 squared plus omega 2 squared, which we've worked out to be phi dot squared sine squared theta plus theta dot squared. And then we had a plus 1/2 times the rotational inertia about the symmetric axis, omega 3 squared, and I'm just going to leave that as phi dot cos theta plus psi dot squared. So that's our kinetic energy. The Lagrangian, maybe we'll write it over here, the Lagrangian is the kinetic energy, which in this case is just rotational, minus the potential energy, which is the gravitational potential energy. And so when we combine everything, just writing out exactly the rotational kinetic energy again with no changes. And then if you recall, we had an mgh cos theta for the potential energy. And so all we're going to do is we're going to subtract off that potential energy. So it's minus mgh cos theta. Okay, so that's our Lagrangian. So we'll eventually be talking about angular momentum, and we're going to use L for angular momenta as well. So let's just make it clear that this is the Lagrangian. Okay. One thing before we do that, let's say our Lagrangian is in terms of 3 generalized coordinates, and those generalized coordinates are the Euler angles. Coordinates, and they are phi, theta, and psi. Okay, so remember we had conjugate momenta defined as well. So the conjugate momenta are, so we would have a p phi would be dl d phi dot, and p psi would be dl d psi dot, and we'd also have a p theta, which would be dl d theta dot. And if you recall, we had this condition that if, say, dl d theta, let's do phi. If dl d phi was equal to 0, then this conjugate momenta is conserved. It's easy to see where that comes from. Let's just remind ourselves that the equation of motion for the generalized coordinate phi, equation of motion, was given by dl d phi minus d by dt dl d phi dot. And those two had to be equal to 0. So if dl d phi is equal to 0, and we write dl d phi dot is equal to this conjugate momentum, then we would have 0 minus d by dt of p phi is equal to 0. And so the only way that that could be true is if p phi is equal to a constant. Okay, because we're taking a time derivative, and we need that time derivative to be 0. Okay, so good. So that's a little bit of a kind of a quick review. So let's go back and let's look at our Lagrangian, and let's make some observations. The Lagrangian depends on phi dots. There's a phi dot here, and there's a phi dot here, but there's no phi terms. So we could say L is independent of phi, therefore dl d phi will be 0, and we expect p phi to be equal to a constant. So we're going to get one constant of our motion as the conjugate momentum p phi. We could do the same thing for psi. There's a psi dot, but there's no just psi, and so L is independent of psi. Therefore, dl d psi is equal to 0, and p psi is equal to a constant. L does depend on the theta variable, so the conjugate momentum p theta is not a constant of the motion. But we have already identified two constants of the motion. Okay, so the p phi is equal to dl d phi dot is equal to a constant, and p psi is dl d psi dot is equal to a constant. Remember also what we said is that if the generalized coordinate was a length, then the conjugate momentum was regular momentum in units of, say, kilograms meters per second. If the generalized coordinate was an angle, then the conjugate momentum is an angular momentum. And so these are conserved angular momenta. Okay, so let's start let's start by taking the derivative of the Lagrangian with respect to psi dot. That's the easier one. Maybe what we should do is, instead of scrolling back and forth, let's just rewrite our Lagrangian so that we have it here. So I'm going to write it exactly the way that we had it above. And then there's a minus mgh cos theta. Okay, good. So let's do p psi, which is dl d psi dot. And so we just have to do chain rule. And so we're going to get a is and then phi dot cos theta plus psi dot. And then we take the derivative of what's inside with respect to psi dot, and we just get a 1. And so that's it. So this is a constant. So this is one of the constants of our motion. Okay. And let's do p phi, which is dl d phi dot. Okay, and so what do we get? We get an I phi dot sine squared theta plus, and then we have to do this chain rule again. We get is phi dot cos theta plus psi dot. And then by chain rule, we take the derivative of what's inside. We'll pick up a cos theta factor. Okay, so that's fine, but this right here is exactly what we just wrote down for the conjugate momenta of the psi coordinate, and so that's a constant. Okay, so this has to be equal to a constant, and so therefore we have p phi is equal to I phi dot sine squared theta plus p psi cos theta, and that's equal to a constant. Okay, good. So let's see if we can attach some kind of physical significance to these conjugate momenta, these angular momenta, in fact. So let's recall the following. Recall that the angular momentum about let's say about the symmetry axis. So the symmetry axis is one of the principal axes. And so our symmetry axis was the z-axis, which is the E3 hat direction. And because it's a principal axis, its angular momentum is very simple to write down. It's just the rotational inertia times the angular velocity. And so we have to take the rotational inertia about that axis, which is about the symmetry axis, and we multiply it by the component of the angular velocity along that axis. We've already used omega 3 earlier in this video, and we had written down that it was phi dot cos theta plus psi dot. And if you look, this is exactly p psi. And so this is exactly equal to p psi. Okay, and so therefore the conclusion we could make, therefore p psi is the angular momentum about the symmetry axis. and it is conserved, or it's a constant. Okay, good. So we can just put this in a box. What I'm going to do is I'm going to insert that picture once more of the Euler angles. And so let's see if we can pull it up here. Cancel. Okay, there it is. And so here is our z-axis, which is our symmetry axis. And notice that phi dot, this angular velocity, is along that axis. And so what that tells us is that the conjugate momenta, or the conjugate momentum psi, corresponds to the angular momentum about the axis that psi dot points along. So note, note that psi corresponds to the angular momentum along the axis that psi dot points. Okay, well, the same thing is true of phi dot. And so we could say likewise, p phi corresponds to the angular momentum along the axis that phi dot points. And this axis that phi dot is pointing along is the z prime axis. It's the fixed z axis. It's the z axis of our fixed coordinate system. So this is z prime, and so this is in our fixed coordinate system. And so this is the z prime axis. Okay, so that means the angular momentum along the z prime axis is equal to this p phi, which is equal to I phi dot sine squared theta plus p psi cos theta, and that's equal to a constant. And this is also p psi, we've determined, is the angular momentum along the symmetry axis. Okay, so that's the physical significance of these two conserved quantities. If we go back to our Lagrangian, there it is. We've now dealt with the generalized coordinates phi and psi, but we still have the theta generalized coordinate. And we haven't dealt with that one. We've already argued or proposed that the dl d theta is not zero, and so we wouldn't expect the angular momentum associated with the theta coordinate to be conserved. So let's deal with the third generalized coordinate, theta, and the equation of motion for the theta coordinate is going to be given by the usual expression. And so we have to evaluate these two partial derivatives. So I think what I'm going to do is I'm once again going to write down the Lagrangian so that we have it in front of us. Okay, and so here we go. So L was equal to 1/2 I phi dot squared sine squared theta plus theta dot squared plus 1/2 is phi dot cos theta plus psi dot squared minus mgh cos theta. Okay, good. So that's probably the last time we'll have to write that down. Okay, so dl d theta. So there's a few terms that we have to get right here. So we're going to have, let's see, an I phi dot squared, and then we have sine squared. So when we take the derivative, we get 2 sine theta. The 2 cancels with the 1/2, so we get a sine theta. And then we have to take the derivative of sine theta, so we get a cos theta. And that's that. And then we have to do chain rule over here. So we have is phi dot cos theta plus psi dot. And then we have to take the theta derivative of what's inside. So we'll pick up a minus phi dot, and then we get a sine theta. Okay, and then we have mgh cos theta. The cosine becomes a minus sign. We have a minus sign out front, so we get a plus mgh sine theta. Okay, dl d theta dot is, I guess we have only one theta dot. Is that right? Yes, so we get an I theta dot. And so that means that d by dt of dl d theta dot is going to be I theta double dot. Okay, so then the equation of motion, dl d theta minus d by dt of dl d theta dot equals 0 becomes, okay, so mgh sine theta plus I phi dot squared sine theta cos theta, and then we have a minus, so this is minus is theta dot cos theta plus phi dot, and then we get a phi dot sine theta, and then that has to be equal to, so we would have a minus I theta double dot equals 0, or we could just say that's equal to I theta double dot. This thing out here is just the psi. It was that angular momentum about the symmetry axis. Okay, so rewriting this then, we have, sorry, maybe I have a, do I have the sign right? Yeah, I think that's okay. Okay, good. So then we have mgh sine theta plus I phi dot squared sine theta cos theta minus p psi phi dot sine theta is equal to I theta double dot. Okay, so let's call this equation number sign, and we're going to come back to that in a little bit. But anyways, that's the analysis of the Lagrangian. And so we got our 2 conserved angular momenta, and we've got our equation of motion for theta. Okay, so what I want to do is I want to go back to this angular momentum about the fixed z-axis. And what we're going to do is we're going to take a derivative with respect to time, and we're going to say that that has to be equal to 0 because we said that this was a constant angular momentum. Okay, so let's do that. So let's consider dLz prime dt and say that that has to be equal to 0. So that's going to be d by dt, and let's write down Lz prime. So it was an I phi dot sine squared theta. So it's an I phi dot sine squared theta. And then we had a plus p psi cos theta. Plus p psi cos theta. And then we need that to be equal to 0. Okay, so this is a constant, right? So we know that that's a constant. So when we do this derivative, I'm just going to write it as I, and then we're going to have d by dt phi dot sine squared theta. And then we distribute the derivative, p psi is a constant, and then we have the derivative of cos theta, which is, so let's see, cos theta becomes a minus sine theta, and then we have to take the time derivative of theta, so we get a theta dot, and so this has to be 0. So I'm going to call this star. So now we have equation star and we have equation number sign, and we're going to come back to both of those. Okay, so now here's where I want to make a connection to the bicycle wheel demo. And so the bicycle wheel is a symmetric top. So it has a symmetry axis, which we'll call the z-axis in the rotating frame. And then it has rotational inertia that perpendicular to that are equal. I1 is equal to I2 is equal to I. Okay, so when we did this demo, what we did is we spun the wheel really fast, and then we hung it from its axle so that the string that was attached to the ceiling was our z prime axis, and when we hung the bicycle wheel from that string, we kept the axle perpendicular to that string. Okay, so if I was to draw a picture, what it looked like is our string was our z prime axis in the fixed frame, and then we had a symmetry axis where if this is our, actually let me draw it this way. So this is our bike wheel or our symmetric top, whatever you like. It was like this. This is our symmetry axis, which is the z-axis or the E3 hat direction. And the angle theta is the theta between these two z-axes in the rotating frame and the fixed frame. Okay, and then what we have is we have a gravitational force acting on the center of mass of our bike wheel. Okay, so in this case, when we set this up, our initial conditions at time t equals 0 are, well, theta, let's say theta 0 is the value of theta at t equals 0, is pi by 2, it's 90 degrees. And when we hung the wheel onto the string, we released it from rest. And so that means that initially at least theta dot at t equals 0 is equal to 0. Okay, So those are our initial conditions, and what we're going to do is we're going to go back to equation star, and we're just going to put those initial conditions in. When we put in the initial conditions that theta is pi by 2, then sine theta just becomes a 1. And then we have a theta dot over here, which at t equals 0 was equal to 0. So this theta dot is going to vanish, and the sine thetas are going to become 1s. Okay, so therefore at t equals 0, star becomes, let's see, theta dot goes to 0, sine theta goes to 1. Okay, so we just end up with I d by dt phi dot. And there's nothing else, right? Because the sine theta becomes a 1 and the theta dot becomes a 0. And so this has to be equal to 0. And so therefore, what we get is phi dot is equal to a constant. Okay, so then for our initial conditions, phi dot never changes its value. Okay, so let's go back to, let's return to equation star for some time greater than 0. So we'll just write out the full expression for equation star, which, remember, came from a time derivative of one of the constant's angular momenta. Okay, so now the new information that we have from our analysis of the initial conditions is that for the initial conditions that we chose, phi dot is a constant. That's why I didn't evaluate this derivative from the beginning, is because I wanted to get this information first. And so that means, therefore, that if phi dot's a constant, we can take it outside the derivative. And so the derivative just acts on the sine squared theta. And then we have minus p psi theta dot sine theta is equal to 0. Okay, and so now we evaluate this derivative. And so we would get 2 sine theta cos theta theta dot if we do all of our chain rules properly. Okay, so what do we have then? We have 2I phi dot sine theta cos theta theta dot minus p phi theta dot sine theta is equal to 0. So there are some common factors. We have a theta dot sine theta, and we have a theta dot sine theta. Okay, so we have 2I phi dot cos theta minus p psi, and then we have theta dot sine theta is equal to 0. Okay, so my claim is that this stuff in brackets is not 0. Okay, so for example, how could we prove that? For example, let's take the t equals 0 case of theta is pi by 2. Okay, then that means the cos theta is equal to 0, and therefore the brackets are become just the minus p psi. Okay, now what was that angular momenta? Let's look it up. Let's see if we can find it. It's not that one, it's this one. So it's is theta dot cos theta, is phi dot cos theta psi dot. So that was equal to is phi dot cos theta plus psi dot. But we're thinking about the t equals 0 case, so theta is pi by 2, cos pi by 2 is 0, and so this is equal to minus is psi dot. And if we had a spinning bike wheel, then the angular momentum about the symmetry axis is just determined by the angular velocity about that symmetry axis, which is just how fast the bike wheel is spinning. So we're assuming that our bike wheel is spinning, okay? And so that's at least one instant in time where the stuff in brackets is not equal to 0. So the only way that we could satisfy this equality then is by forcing theta dot to be equal to 0. Okay, because sine theta is not equal to 0 when theta is pi by 2, sine theta is equal to 1. So we can only satisfy this equality if theta dot is equal to 0. Okay, but we set initially theta dot, we initially set theta to be pi by 2, and if theta dot's 0, that means theta stays at pi by 2 for all time. Okay, so therefore theta is equal to a constant, and if theta 0 is equal to pi by 2, then theta is equal to pi by 2 for all times. Okay, well, what that means is that the angle between our fixed axis z prime and the symmetry axis, so we had here's our top, right? And so here's our spinning top or our bike wheel or whatever it is. And so this is z, and theta is the angle between these two axes. And so theta is equal to pi by 2 for all times. And so if the angle theta is not changing, the only possibility for interesting motion is that we have a rotation around our fixed coordinate systems. Of course, our top is spinning around the symmetry axis as well. And so this is, remember, the direction of the phi dot, and this is the direction of the, this is psi dot, and this is the direction of phi dot. Okay, so the last thing we want to do is to see if we can determine, let's determine phi dot, which is the angular frequency that the symmetric top processes about the fixed z prime axis. So this is something that an observer in a fixed reference frame, an inertial reference frame, would see. They would see the top processing around the z prime axis, and so what we'd like to do is see if we could calculate the angular frequency of that precession. So this is where we're going to return to that equation of motion for theta. So we return to number sign. You know, we're trying to find something out about phi dot. And to do that, we're going to use this equation of motion of theta, and because it contains the phi dot we want. So here's that number sign equation, the equation of motion. And so I'm going to rewrite it again. Okay, so I'll just rewrite it exactly as it was. So it's mgh sine theta plus I phi dot squared sine theta cos theta minus p psi phi dot sine theta was equal to I theta double dot. So that looks like a bit of a beast. It's complicated, but there is a lot of simplifications. So we know now that theta is pi by 2. So wherever we see a cos theta, that's going to be 0. Wherever we see a sine theta, that's going to be 1. We also know that theta dot is equal to 0, and so therefore theta double dot is also equal to 0. Okay, and so all these simplifications are, this becomes 0, this becomes a 1, this becomes a 0, and this becomes a 1. And so what we're left with then, in our case, the equation of motion for theta becomes, so maybe I should just say the equation of motion for theta, which was number sign, becomes mgh minus p psi phi dot is equal to 0. So that's nice and simple. And so therefore phi dot is equal to mgh divided by p psi. And so that was just the angular momentum about the symmetry axis. And we've already worked out previously that when theta is equal to pi by 2, this angular momentum is just is, the rotational inertia about the symmetry axis, times psi dot. And so what we have is mgh is psi dot. So let's just recall psi dot is the angular velocity of the top or bike wheel spinning about the symmetry axis. Okay, so what that tells you is that the precession frequency, so this is the precession angular frequency. So it's the precession, maybe we should be more detailed. It's the precession about Z prime. Let's write this in a more clear way. This is the angular frequency of the precession about the fixed Z prime axis. Our symmetry axis was the Z axis of the rotating system. Okay, so we could change that frequency of precession by changing, for example, the torque mgh that's acting on the symmetric top or the bike wheel. And if you recall, if you think back to that first day of classes when we did the demo, we had the bike wheel precessing and then we added some additional weight onto its axle, and that increased the torque, and we saw the thing process with a shorter period or a higher frequency. And so that's exactly predicted by this expression. What this expression also predicts is that as you change the rate at which the wheel is spinning about its symmetry axis, that would also change the precession frequency. Just as one last detail, the period of precession would be 2 pi divided by phi dot, which would be 2 pi is psi dot divided by mgh. And so this is the precession period. Okay, good. So that's what I wanted to say about the symmetric top rotating about a fixed point. We saw that there was 2 angular momenta which were conserved. There was the angular momenta about the fixed z-axis and angular momenta about the rotating symmetry axis. And for the special case where the top symmetry axis starts perpendicular to the fixed z prime axis, we've gone and calculated the precession frequency. If you don't recall all the details of this video, what I'm going to do is in the description of this YouTube video, I'm going to put a link to another YouTube video. And it's the exact same demo we did. In fact, I copied the demo from this video, and they do it better than I did it anyways. So if you want a refresher, I think the linked video is about 3 minutes, and so you can look at this bike wheel demo once again and try to connect it to the analysis that we've done here. All right, so that's that. There will be one more video, and we're going to talk about the stability of rotations of a rigid body about its principal axes. Okay, good. Thanks you very much, and we'll talk to you later.